Hi, I'm Adam. Welcome back to Godot Game Lab. In this video, we'll do a bunch of new stuff introducing the UnitGrid, the PlayArea, and the TileHighlighter components to the raster. The problem is, I can't really show you much because it's more like a structural thing, it's not that flashy, but the TileHighlighter itself is quite visible. So we have this defined PlayArea, which is 4 columns by 7 rows. And you can see that if I hover over the valid cells inside that area, it will be highlighted which cell I'm hovering over. And the same is true for the bench, which is 10 columns by 1 row. Also, if we go to the remote scene tree and expand these things, I can show you that we do have this unit grid where we define the size of the unit grid inside our game world. And we do have a dictionary which will store all the units attached to the coordinates. So you can see that since we have no units added here, these values will be null. And we do the same for the bench. So we can define the size of the bench, which will be 10 columns by 1 row. And it does have 10 available spaces for the coordinates. I know this doesn't look too interesting or inviting, but these are very crucial to the core part of the game. So let's jump into it. So we have a bunch of new things we do in this video. First of all, we'll introduce the PlayArea script, which will build on top of the existing tile map layer node. This will be like an API to work with tile coordinates inside our game space. So what does this mean? It means that the PlayArea itself doesn't really do anything interesting, but it provides a bunch of public methods which other components or classes can rely on. And we talk about much more in detail about those methods when we implement them. So we have 2 of these play areas inside our game. We have the bench and we have the game area itself. We'll also add 2 new components under the play areas. One will be the TileHighlighter, which you can see on this GIF. So when we start dragging a unit, for example, we'll highlight the tile which is currently being hovered to make it easier to navigate dropping units on the battlefield. And this TileHighlighter component will very much rely on the PlayArea's API to have access to those methods which work with coordinates. And the other component we'll have is the UnitGrid, which is a very central part of the whole game architecture. It basically stores the grid size for an area where units can appear, right? So in this case, the bench and the game area. And it not just stores the grid size, but also the current unit information. It will be pretty much like a mini database containing the current values or the current information about units inside that grid. So we'll store this information in a dictionary where the keys will be coordinates inside that grid and the values will be the unit instances which occupy those coordinates. And inside the unit grid, we can do a bunch of things like adding units, removing units, getting all the units, or checking if a tile is occupied and things like that. It will also have a signal called UnitGrid changed, so we can notify all the other systems inside our game when the UnitGrid is changed for whatever reason. And this will be very useful, for example, for updating the UI, for activating traits or checking the team size which currently occupies the game area. So let's see how we can add all this to our game. So I have my project open here, but before we can actually jump into the new stuff, I made a mistake like I usually do. So let's see what is this mistake and how we can fix it. So first of all, if we run the game in its current state, the velocity-based rotation works fine, right? Well, yes, but only because in Godot, vertical synchronization is enabled by default. So if we jump back to Godot and go to the debugger and go to monitors, you can see that the game is locked to run in 60 FPS. So it does work, right? I can drag my unit around and everything looks fine. But as soon as we turn off VSync and we get more FPS on the game, that's when things fall apart a little bit. So let's go to project and project settings. And if we search for synchronization, then under display and window, we should find VSync mode. And it's enabled by default. So if we turn this off and say it's disabled and run the game again. Now if we go to the debugger tab and go to FPS, you can see that I get a couple of thousand FPSs. So Now the rotation won't work at all. No matter how fast I try to rotate my guy here, it won't work. The question is why, right? So let's go back to the script tab and we can hide the debugger for now. And we can press Ctrl-Alt-O and open up our velocity-based rotation script. So the problem is we run the whole logic inside our process function, which runs every frame, right? And we calculate the velocity of the unit by subtracting the current global position of the unit and the position in the last frame. See, the problem is the faster the game runs, the more frames we have, the smaller distance we travel in a frame. So you can see that we set something like 3 for the X velocity threshold. And when the game runs with 60 FPS, it's a good value because it's pretty easy to go over this threshold as 0.01 second elapses between the two frames. 1 divided by 60, right? But when we have 2000 FPSs, much less time elapses between the two frames, which means that the unit actually travels much less between the two frames. So this way of checking the threshold is not the best, because the more FPS you have, the less likely you go over the threshold. That's one thing. Another problem is that when we calculate the angle, I multiplied this rotation multiplier by delta, saying that this makes it frame rate independent. Well, in this case, it doesn't really do that because we want to calculate the angle we are aiming for regardless of the FPSs in the game, right? And what delta does is it tells us how much time passes between two frames, between this frame and the last one. So again, the rotation value will be based on the FPS of the game because the final angle will be calculated with this delta value. So we definitely don't need that. But just by deleting this and saying that, okay, the angle doesn't really depend on the time between two frames, we still have the problem because when I run the game, the velocity calculation problem still persists. So if I'm really fast, you can see that the rotation happens. But if I'm moving the unit in a normal speed, in a sort of normal speed, that it doesn't really register that it should rotate. So somehow we need to make this velocity calculation time-based instead of frame-based, if that makes sense. So we have two options here. We can either do something like, let's say that we calculate the velocity not between this frame and the last one, but 2 points in time. So let's say we take the target's global position now and compare it to not the last frame's position, but the position where the unit was, let's say 0.25 seconds earlier. Hopefully you see the difference, right? So instead of using 2 frames, we use this frame and we use a point in time in the past to compare those two. But that's a little complicated for the issue, so actually one of my Coffee supporters who pointed this out suggested an alternative solution, which is much easier to implement. It's a bit of a cheat, but works pretty well for this use case. So what we can do is we can use not the process virtual method, which runs every frame, but we can actually change this to the physics process virtual method. So what's the difference between the two? The physics process is by default logged into 60 FPS. So while the frame rate of the game might fluctuate or change, right? It can be 3000 FPS, but when I open up another game, it might drop to 1000 or something like that. So what most game engines do is that they have a different process for rendering frames, and they have a different process for dealing with physics-based simulations. And so if we want the physics-based simulations to be consistent, they have to be locked to an FPS value, so they can't really fluctuate. And this is what exactly this physics process does. So when we try to use the physics process callback instead of the process callback, this delta value will be most likely consistent. So the game engine tries everything to lock this physics simulation process loop to 60 FPS by default. It cannot go over 60, but it can go under 60 if the frame rate drops below that. That's not an issue, however, for us because we actually have a problem with too high FPS values, right? We saw that because then this distance becomes too small to notice. So if we use physics process, then we can sort of cheat the whole thing. And even if the game has like unlimited FPSs, we don't lock it with vsync, then we can still use the physics process to say that, okay, for these velocity calculations, we are much better off using the physics process, which is locked to 60 FPS by default. So just by changing this, if we run the game again, I might have a couple thousand FPSs again, but the rotation will work the same, even though it looks a bit funky and it rotates way too much, because if you remember, we deleted this times delta from the angle calculation. But the rotation works again and will go over the velocity threshold. And if we go to project and project settings, you can actually search for physics process. And if we go to physics and common, I believe, yes, that's where you can change the physics ticks per second. So it's 60 by default, but you can use any value you want. And it says exactly that. So this controls how often physics simulation and node.physics process methods are run. 60 is fine for this kind of game, I think. And then we can use the same solution. So again, the other version would be to implement a time-based velocity calculation instead of a frame-based one like we use here. And another thing I kind of realized is that this rotation multiplier doesn't really make any sense. So how do we expect to know what kind of value we get, right? Lerp angle uses radians, but for us mortals, it's much easier to think in degrees. So how about we make a little quality of life change for this component while we're at it, and we change this from rotation multiplier to something like max rotation degrees, which makes much more sense, and we can change it to something like 50 by default or whatever. And if we use degrees, we can do something like we take the normalized velocity and then we can multiply it not with this rotation multiplier because it doesn't really exist anymore, but with our max rotation degrees value. See, the problem with this is that it will be way too much for radians, but we can easily convert between those two. So we can say, instead of rotation degrees, you can say deg to rad, which will be a method that converts between the two. So we'll say that, okay, let's just convert these degrees to radians because we know that this lerp angle uses radians to do the rotation, but then we can use degrees in the editor, which makes it much easier for us. And if we save this with Control S and go back to 2D view and go to the units scene, we can select the velocity based rotation and we can set whatever value we want. Because we overwritten it, we can see how that looks like if we run the game. And you can see that the 50 degrees is about right. If I start to drag it, I think it's a bit too much actually for my liking. So we can just change it to whatever value we like. And this will be in degrees. So the maximum rotation we can achieve will be 30 degrees. Yeah, and this feels much, much better to me. So first of all, we fixed the issue we had. So by using the physics process, we tie it to this 60 FPS, and if we turn off vsync and have much more FPSs in our game, it still works. And we also made a quality of life change, and we made these components use degrees instead of radians and do the conversion ourselves. So again, thanks for pointing out the issue, and I'm glad we were able to make the code much better and reliable. For now, I'll just go back to the project settings and re-enable vsync because it won't be an issue anywhere else in the game. So it can be locked to 60 FPS. Okay, now we can move on to actually implementing new stuff next. So the first thing we gotta do is the UnitGrid. So we can store data about units and the size of those grids as well. Let's go back to 2D view and go back to our arena scene. And this is where we'll add our unit grids. But first we need to create this component. So in our file system docs, select our components folder, right click, create a new script, and we can call this unit_grid.gd. We can turn off the default template and we can create a new one. Double click to open this up in the editor, and let's see how we do this. So the first thing we do is we provide a custom class name called UnitGrid. Then we'll have a signal when the UnitGrid changes. So again, later down the line, when we want to update the trait UI or the team size UI, we can rely on this information when the game area's UnitGrid changes. Then we have one export variable for the size of the unit grid, meaning how many rows and columns it consists of. This is not a vector 2, but a vector 2i. The only difference between the two is that vector 2i can only have integer x and y values, which is perfect for us, right? Because we don't want to use fractions for coordinates. Then we have a dictionary which stores the unit information itself. Again, the keys will be coordinates, so vector 2i's, and the values will be either null if there is no unit on the given coordinate, or a unit instance, right, which is instantiated and occupies that space. So inside our ready callback, what we do is we initialize the dictionary. So we need a double loop for this one. We iterate through all the x positions, then all the y positions, and say that the unit dictionary's value should be null in that given coordinate, this key, right? So we take the coordinate, create a new vector 2i on the current position. So for example, for the first one, it will be 0, 0, and say that, okay, at 0, 0, there's no unit. And we do this for all the available positions, because when we run the game, all the grids will be empty. Then we'll have a method to add a new unit, register a unit inside our unit grid. We need two parameters for that, the tile we want to occupy and the unit instance itself, which will be, I just used a note here, but it will be a unit, right? So we say that the dictionary at this position we have as a parameter should store this unit, right? And then we just emit the unit grid changed signal to make sure that we notify everyone that, okay, something happened, the unit was either added or removed. Then we again have a public method to check if a tile is occupied or not. It's pretty easy. We just take a coordinate as a parameter and we return a boolean, right? So we just get that unit value from our dictionary at the tile we are currently checking. And if it's null, then it's not occupied. But if it's not null, then it's occupied. So we say that, okay, if at this position something is there, meaning it's not equal to null, then the tile is occupied. Otherwise, it's not. Then we also have a boolean to check if the whole unit grid is full or not. Again, we return a boolean, and we can use a cool new method from Godot 4. We just say that we take our units dictionary, grab all the keys, and this method, if we press and hold Control and click on it, it returns an array of the keys, right? And if you think about it, this array of keys will be vector 2i's, all the coordinates we have. And for arrays, we have this method called all. Again, if we press and hold Control and click on it, calls the given callable on each element in the array and returns true if the callable returns true for all elements in the array. So if you take a look at this example, if we have this array of 6, 10, and 6, and call this greater than 5 method for each and every one of them, it will return true, because what this method does is it checks if the number is greater than 5 and then returns true, otherwise returns false. And you can see that it returns false in other cases where we have 1 or 0 where this is true. So we use this to a very similar check. We grab all the coordinates and call this isTileOccupied method, which we just created up here. And if all of them returns true, that means the whole grid is full, right? Each and every coordinate is occupied. Then we have a method called getFirstEmptyTile. This will be super useful when we buy a new unit from the shop. We can use this method to get the first empty tile inside our unit grid. So because this returns a coordinate, the return value will be a vector 2i. And what we do is we iterate through all the keys inside our dictionary. And if we find one which is not occupied, so again, we use this isTileOccupied method. If we found one which isn't occupied, then we can return this coordinate because we found the first empty one. But it can happen that the whole unit grid is full. And if that's the case, we get to the end of this for loop and we haven't returned anything, right? So if that's the case, it means that the grid is full, so there is no empty tile. And we can do a bunch of ways to sort of signal this. We can either use a null value, but what I did here is I returned -1 and -1 for both of those coordinates. And we know that this is not a valid unit position. So if this method returns this value, it means that the whole thing was full. This is just because all the code paths need to return something. We can definitely do safety checks with isGrid full as well later down the line, but we just need to somehow return something even when there's no empty tile left. And the final method we have is called getAllUnits, and it returns an array of units. So what we do is we create this new array of units, which will be empty by default. And then we iterate through all the values inside the dictionary because we don't really care about the coordinates in this case, right? So we grab all the values, and those values will be either null values or valid unit instances which occupy coordinates inside our grid. So with this if check, we just make sure that it's not null, right? This will be false when we have null, but if it's not null, meaning that it's a unit, then we can just append it to the array. And when we're done with the whole for loop, we can return this new array from this method. And that's really the first version of this UnitGrid. So we can save the script with Control S. I hope it's not too bad. And if we go back to 2D view, we can now actually create these unit grids, right? So let's select the game area. This is this one, right? Where the whole gameplay and fights will happen. And we can just click on the plus sign to add a new child node. And since we're dealing with coordinates inside our 2D game world, we can't really add a simple node because nodes don't have coordinates inside the game world. But node 2Ds do. So we'll use a node 2D this time. That's why we extended the UnitGrid class from node 2D, because they do have a transform, right? The position, rotation, scale. Mind you that nodes do not have this. So if we want to deal with positions inside the game world, then we need to use node 2D or node 3D. So let's rename this to Arena Unit Grid. And what we need to do is we drag and drop, right, the script. And we need to set the size. We use the same coordinate system that the tile map uses to make our lives easier. And it might be a bit confusing because I for sure thought that X will be the number of rows we have and Y will be the number of columns. But for tile maps, this is swapped. So X will be the number of columns we have and Y will be the number of rows. So in the case of the game area, I want the player to use unit grids in 4 columns, the first 4 columns and all the rows. So this size will be 4 by 1, 2, 3, 4, 5, 6, 7. Okay. I know it might be a bit confusing, but it makes our lives much easier because the tile maps use the same coordinate system. So when we get the hover tiles later on this video, it will be much easier to do it like this. Okay, so we have the arena unit grid and we do the same with the bench. So select the bench node, click on the plus sign or press Ctrl A. We'll use a node 2D. We can double click on this and rename it to bench unit grid. And we can just drag the script again. So this is our bench. It will consist of 10 columns and 1 row. So 10 by 1 in this case. Okay, so that's pretty much all we need. We can save the scene and run the game, but nothing really happens, right? So we cannot really test this for now because this is sort of like a data holder for the units. If we go to the remote scene tree and open up our game area or the bench, you can see that we have our grid here and we have our dictionary, and the whole thing will be full of nulls because we don't really have any units registered, right? And the same for the bench, but the dictionary will be much smaller because we only have 10 available slots. So it kind of works, but it would be nice to test it, right? So let's go back to the script and see how we can test this. So we can test this inside our ready function. We can do something like that. We just take a look at our scene tree here, grab one of these units and drag it right here and drop it over our ready callback. And we don't really have to press Ctrl this time because we just want the node path to the unit. And we can call the add unit method and add it to a tile of our liking. I just use the first one, which will be at 0, 0. Like this. So with this line of code, we said that, okay, the first unit should be added to this 0, 0 position. So we can test the add unit method if it works or not. And then we can do a bunch of checks. So we can call the isTileOccupied for that position to see if it works. We can check if the grid is full, get the first empty tile, which should be the second one, right? Because the first one just became occupied. And we can test the getAllUnits, which should return an array of 1 because we added 1 unit. We can test all these methods inside our console with a small trick like this. And if we run the game, we get a bunch of messages here, right? So isTile occupied will be true in both cases. We have two sets of messages because we have two unit grids, right? Then the isGrid full will be false for either of those. The array of all units will contain the same unit. It has the same ID, and that checks out because we use the same unit from the scene tree. And the first empty tile will be different for the two grids, which is perfectly fine. If we take a look at our remote scene tree while the game is running, we can check the arena unit grid. If we expand this dictionary, you can see that the first coordinate is 0, 0, and there we have our unit registered. And the next in the dictionary will be 0 and 1, which means the same column, but the next row. So for this one, this will be considered the first empty position. So that works. But for the bench unit grid, if we expand the dictionary and scroll down a bit, you can see that we only have one row here, right? So the column index will change. 0, 0 will be occupied, which is this one. And then the first available position will be 1 and 0 in the next column, which checks out. Awesome. So everything works perfectly fine. We can stop the game and go back to the script tab. And just to make sure, we can get rid of these testing methods once we are convinced that everything works as intended. So we can save the unit grid with Ctrl S, and that's one component done. If you like my content, please consider checking out my Ko-fi page, where you can donate one time or become a member and get early access to all my content and videos. Okay, so now that we have our unit grid ready, we can create that PlayArea script, which will give us this API to work with coordinates. So if we go back to 2D view for a second, you can see that our game area and our bench are both tile map layers, right? So this is what I was talking about when I said that we want to extend the functionality of our tile map layers. So we'll kind of use them as components as well, where they are tile map layers, but we give them some extra oomph, some extra functionality. So let's select our components folder in the file system doc, right click on it and create a new script. And let's call this play_area. Create the script and double click on it to open it up in the editor. This will be pretty easy to code, but I'll explain what each of these methods can be used for in detail after we're done with the coding part. So first of all, let's create a custom class name and call it PlayArea. Then we'll have an export variable where we can attach that unit grid component to this PlayArea. So why do we need the unit grid component? The reason is pretty simple, because for the PlayArea to work and for us to be able to work with coordinates, we have to know the bounds of the PlayArea. And for this, we'll use a rect2i, which is basically a rectangle, which has a position and it has a size, right? So this is pretty useful because rectangle 2s have methods which we can rely on, which I'll get back to in a second. So in order to determine the bounds of the PlayArea inside our ready callback, we can create a new rectangle which starts at 0, 0, meaning the position of the tile map layer, and it has the size of the unit grid, which is another vector too. So what does this mean? Let's hop back to 2D view for a second, and let me show you. So for the game area, for example, we know that we have our tile map layer here. So that's the position it has, and it's 0, 0, right? And we know that we have 4 columns and 7 rows. So we say that we start drawing a rectangle here, and the end point of the rectangle will be this one, which is at 4 and 7. 4 columns and 7 rows, right? So if we have the starting point and the end point, we can basically just draw in the rectangle, right? So if we know these 2 points, we can say that this is the rectangle we have, right? This is the starting point and this is the end point, or the size of this rectangle. So this is how we can define rectangles in Godot. And that's perfectly fine for us because these are the valid tiles, right? So it will be much easier to check the bounds of the PlayArea if we have this rectangle defined. So for this, we actually need the unit grid, because that's where we store the grid size. We could have done something like creating a new export variable here, which again will be a vector2i, and use the same size. So why do you think that's not a good solution? Why is it better to reference the unit grid here? Well, it's because it's more error prone, I think. redundancy or repeating the same things is something we usually want to avoid in programming. Because if I have to input the same thing in two different places, what can happen is that, okay, I decided I want another column or one less column for the unit grid, right? So I have to remember as a designer that I have to replace those values in two different places, in the unit grid and in the play area as well. And that's a problem because if I forget to do it in one place and only do it in the other one, then I will have all sorts of different bugs and it will be hard to figure out why it isn't working as intended. Whereas in this case, we say that, okay, the unit grid is responsible for setting up the size of that grid, and the play area can just rely on that same value and use the same value to make sure that everything works and we avoid redundancy. Hopefully that makes sense. So the next method we provide, so this is what I meant by API. These will be all very simple one-line public methods which can be used by other components later on. So we have one called getTileFromGlobal, and what it does is it takes a global position from the game's world and returns a vector to I, meaning a coordinate inside that grid or that tile map. So we use two functions for this one. We use toLocal to convert the global coordinate to a local one. I'll explain this when we have the demonstration. And we use the tile map layer's local to map function, which takes a local coordinate in the game world and converts it into a tile map coordinate. We'll see how this works in a second. Then we have the opposite of that. We have a getGlobalFromTile, which takes a tile position as a parameter and returns a vector 2 for the global position for that tile. And this is useful later on when we want to spawn units, for example, right? Because if I get that, let's go back to 2D view again, because if I know that, okay, this is the first unoccupied tile, so I want to spawn a unit here. Okay, I know the tile coordinate that this is at 0 and 2, but I don't really know where it lies inside the game world. So what are the global coordinates for this, right? Because when I want to spawn a unit, I want to set that global position of the unit to be the same as these tiles. So this method does exactly that. It takes a tile position and returns a global position from it. And we also have a very useful one which we can use for the TileHighlighter component, called getHoveredTile, and what it does is it returns a vector 2i, meaning a tile coordinate, where the mouse currently is. So we grab the local mouse position inside our tile map layer and use the same local to map method to convert it into a tile map coordinate. And we also have one called isTileInBounds, which returns a boolean, and what it does is it takes a tile coordinate and see if it's inside that rectangle we drew earlier. So we use bounds, which is the rectangle, and it has this very handy method called hasPoint. And if we press and hold Control and click on it, it says it returns true if the rectangle contains the given point. By convention, points on the right and bottom edges are not included. Okay, so this is pretty useful because we can check if a tile coordinate is inside that unit grid area or not. And that's useful because if we go back to 2D view again, so if we have this rectangle defined for our area, if I hover over this tile, I don't really want to highlight it, right? Because I can't really drop the unit here. But if I hover over this tile, I do want to highlight it because I can drop it here. So this isInBounds will be true for this coordinate. But even though that this is a valid coordinate inside the tile map, this will be false for this method because it lies outside that rectangle. So this is why we used rect2i for the bounds of the tile map layer or that play area, because it has this really handy method so we don't have to handle this check ourselves. And the good thing is that that's all we really need for this component. So we can save this with Control S. It's pretty straightforward, but it might be confusing all those conversions. So let's see a demonstration of that after actually creating the play areas. So let's go back to 2D view. And we have our game area selected and it doesn't have any scripts attached to it. So let's just select our play area.gd and drop it over the game area. And you can see that we have to set our unit grid component. So if we click on assign, for the game area, the arena unit grid will be the one attached to it. So we just click on OK, and now we have this connection, so we can use the arena unit grid's size property to set the bounds for the rectangle. And we have to do the same for the bench. So select the bench now, drag and drop the script, and assign a unit grid, but this time we'll use the bench unit grid. So make sure that you use the right one. So for the bench, it should be bench unit grid. For the game area, it should be arena unit grid. Let's save this with Control S. And if we run the game, nothing really happens. We don't have any error messages, which is always nice. But we can't really test this in action because, as I said, it's more like an API. So this PlayArea in itself doesn't really want to do anything besides setting its bounds, but only provide these methods for other classes, right? But we can check if the bounds are set correctly. So if we run the game and go to the remote scene tree, we can expand all these things. And if you click on the game area, you can see that X and Y, meaning the position of the rectangle is 0, 0, the width is 4, and the height is 7. Perfect. And for the bench, the width is 10 and the height is 1, which is awesome. Okay, cool. Now let's see how these methods work with a little demonstration. So let me show you first of all the local mouse. What does the local mouse mean? So I use the game area for the demonstration. So we use this tile map layer right here, this one. So since this is positioned here on the map, this will be 0, 0 for the local coordinate or the local mouse position, right? The top left corner. So if I hover right here, then this will be negative because I'm moving left from that 0, 0 point. So when we use get local mouse position, we just say that, okay, we take the node's position and relative to that, we see where the mouse is inside our game world, right? Then we have the global mouse position. So the difference between global and local coordinates is that the global 0, 0 will be the top left corner of the whole game. So if I move my mouse right here, you can see that the global mouse position will be 0, 0 because it's in the top left corner of the game. But the local mouse position will be negative because compared to the position of the tile map layer, we've gone upwards and to the left. But if I move to local 0, 0, then the whole thing kind of inverts. The local position will be 0, 0, but the global mouse position will be greater on both axes as we move away from the top left corner of the screen. So we have the first method. Let me show you this one, get tile from global. So if we see the global mouse position, again, this will be 0, 0 in the top left corner. So you can see that the tile we get is at -5 and -2. And that kind of checks out because we know that the tile map starts here. So if I move my mouse wherever inside the first tile, this method will return 0, 0, right? Because that's the tile at 0, 0. Then we have the hover tile method, which will return to us based on that position, the local position, which coordinate is hovered over currently. So you can see that it works with our game area. This will be 0, 0. And as I move my mouse over, it will properly update the coordinates. So this is why we have this method right here, get hovered tile. It takes the local mouse position, which is this one, for example, 20 and 12, and converts that local mouse position to a tile coordinate, in this case 0, 0. And because our tiles are 32 by 32, you can see if I move my X from 31 to 32, that's when it updates, right? So we have this one as well. And we have inbounds, right? We have this rectangle, which we were talking about, this bounds.hasPoint. We can say that this rectangle is this big, right? So for example, -1 and 0 won't be inside the rectangle. -1 and -1 won't be inside the rectangle either, but 0, 0 will be. 1, 0, 2, 0, 3, 0, and that's where our rectangle ends. So if I move on to the next tile, it becomes false. So I can use this rectangle to kind of check if I'm inside a valid position or coordinate. And this will be super useful for the TileHighlighter component, right? So the TileHighlighter component can use a bunch of these methods here to determine if we should highlight a tile or not. This is what I meant by API. And we can use these methods inside a bunch of different components inside the game. So instead of actually implementing all these inside the TileHighlighter, we say that, okay, this is the responsibility of the PlayArea, And it's a much better separation because we might want to use this one, for example, to spawn units, right? To spawn units inside the game world. We know the coordinate we want to spawn the unit at, and we need to convert that to a global position. So we just say that, okay, this area should be responsible for all these coordinate conversions, and we provide this functionality to all components who need this. Hopefully that makes sense with the demonstration. In itself, the code is not too complicated, but the reason why we need it might be. So I hope that makes sense. And if it does, we can move on to the last part, which is actually using this new API we have to create the TileHighlighter component. Let's go back to 2D view. And we want to attach a TileHighlighter to the game area and to the bench as well. So let's make the component first. Inside our file system docs, select the components folder, right click on it, and create a new script. Call this tile_highlighter.gd. Create the script and double click to open it up inside the editor. The first thing we do is we provide a custom class name called TileHighlighter. Then we'll have a bunch of export variables. First of all, we'll have a property called enabled, which will be a boolean, a checkbox, and it will be set to true by default. It does have a setter function, so when we enable or disable tile highlighting, we can do all the necessary operations. In this case, when we disable the tile highlighter, we want to clear all the highlighted tiles to make sure that it doesn't linger there, right? Then we have an export variable for the play area this tile highlighter belongs to, because we can use the API we were just talking about, right? This can help us determine whether we should highlight a tile or not. We can get the hover tile from it and all those methods we just created. We also have an export variable to a tile map layer, so we can actually draw the highlighted tiles somewhere. Then we also have a vector to I, which will be a coordinate for the tile we want to draw for the highlight. I'll show you this in a second. We also have an onReady variable reference called source ID. I was a bit confused why we need this, but again, I'll show you inside the editor when we're done with the script. And inside our process method, meaning every frame, what we do is first of all do a safety check. So if the component is disabled, we can return from the function immediately. We don't really have to do anything. But if it is enabled, the first thing we do is we use the PlayArea's getHoveredTile to determine which tile is currently being hovered over. Then we do a safety check, again with the help of our PlayArea. So what we do is we check if the hovered or selected tile is within the bounds of the PlayArea. If it's not, then we can clear the whole highlight layer, which means that we erase all the tiles from it and return from the method immediately. But if it is within the bounds, then we call this method called updateTile, which will draw the tile in that given coordinate. That's all we really need to do. So let's implement the setter function and also implement this updateTile method. So for the setter function, what we do is we set the enabled property to the new value we provide when we set it. And also we check if we set it to disabled, so the new value will be false, and we do have a valid play area. And if that's the case, it means that we disabled that tile highlighter component, and we need to clear the layer again to erase all the highlighted tiles. And finally, this updateTile method will be pretty simple. We take the coordinate we want to highlight, clear the whole layer. So if we have a highlighted tile from the previous frame, it doesn't stay there. We can only highlight one tile at a time. And after we cleared it, we use the setCell method for the tile map layer, which uses a coordinate, which will be the hovered tile, a source ID, that's why we needed it, and a tile coordinate. So this is an onReady variable, this is the one we hovered over, and this will be the tile we actually want to paint, which I'll show you in a second. And that's all the code we really need, so it's a pretty short script. Hopefully it makes sense. I know that this source ID and tile might be a bit confusing, so let's see how we need to set this and why. For now, just save the script. The logic itself shouldn't be too complicated though. So let's go back to 2D view. And since this component relies on the methods of our play area, it actually doesn't need to be a node 2D, because in itself, it doesn't really concern with coordinates inside the game world. So we can select the game area, click on the plus sign or press Ctrl A, add a new node, double click and rename this to TileHighlighter. What we need to do is we need to drag and drop the script over, and we have a bunch of export variables now. And we can copy this over to the bench. So I press Ctrl D to duplicate it and just drop it over our bench. And we can just remove that too from the name. Okay, so now while we're here, we can set this one first. So the play area for this tile highlighter, this one will be the bench. And the highlight layer will be the highlight layer under our bench node, this one. And the tile itself should be a coordinate. And to determine this, let's click on our highlight tile map layer so I can explain how this works to you. So the reason why we need the get source ID is because a tile map might have different files, right? So we use this tiles.png to have all our tiles inside, but we might have other ones. So we can drag and drop other files over, so we have multiple sources for our tiles. And this get source ID tells the tile map layer which one we want to use. So we want to grab a tile from this source, the first one. So this is why we use the 0 inside the script. If we go back for a second here, we used PlayArea.tileSet, right? Our tile set is this one, and that's the first source we use. So the get source ID 0 will actually return this one. You can see that it has the ID of 0 right here, this atlas. Okay, and what about the tile? So we have to provide a tile coordinate as well. If I hover over this, you'll see that the source ID is 0 and the atlas coordinates is 3 and 1. And that's the tile I want to paint over the highlighted area. So what we need to do inside our tile highlighter is set the tile's coordinate to 3 and 0, because that sort of identifies that yellow highlight tile we have. And we basically have to do the same for the game area too. So click on the other tile highlighter. We can go back to 2D view, assign the play area, click on this. For this one, it will be the game area instead of the bench. And the highlight layer will be its sibling, right? So the game area's highlight child is the one we want to assign here. And since we use the same tile set, the tile coordinate will be that same 3 and 0. So if we save this with Ctrl S, that's all we really need. We can play the game and we should have our tile highlighter. And you can see that it's enabled. So if I hover over it, we'll get this tile, it updates accordingly. Again, it works if I just use the mouse. And you can see if I go outside the bounds of these areas, everything will be cleared. Like so. Pretty awesome, right? So I think that's it for this video, and I guess I'll see you in the next one. Bye-bye.